In this video, I'll show how some of the new point cloud features can be used in geometry recovery and improvement within the context of topology optimization. On the screen, you can see a topology optimization result from Altair Inspire, including the original design space, the optimization result, and we can also change the density threshold to specify whether we want a thicker or thinner model from the topology optimization. The first step is to extract a mesh from this using the Shrink Wrap tool within the Polymesh tab. Select an appropriate meshing resolution, and then optionally smooth this mesh a little bit to make it a little bit smoother after the voxelization and meshing. Going into the Implicit Modeling tab, we can convert this mesh into the implicit format so we can use all of the tools within the Implicit Modeling tab. It would be tempting to try and offset this model to make it thinner or thicker, but when we use a global value, we often can't find a good offset that suits every area of the geometry. In this context, I'm going to use some of the new features, and in particular the bump feature, to locally offset by placing points, increasing the sphere or radius of influence that the point acts over, and locally offsetting inwards or outwards to open up pores or thicken members. I can also change the fall off to smooth the interface between where I'm editing geometry and everything outside the sphere of influence. Once I've opened up all of the pores I wish to open up, thickened all of the members I wish to thicken, I can also use point clouds alongside the Morph tool to locally select whether I'd like features from the original sharp design space or the thinner optimized result. As with the offset, there's not usually one good value that suits every region of the geometry. So again, we can use a point cloud to locally pick features from each of those models. In this example, I'm going to open up a larger flat surface, which might be good for etching part numbers into or using as a fixturing point or a datum surface. So I will locally ask it to look like the original design space that had a flat face here in this region by setting an appropriate radius of influence, and then also setting this to have a morph value of 1. As you can see, I've recovered the flat face in this region now, where previously I had a truss-like structure. Once I'm happy, I can accept that and progress with this model further down the route of geometry recovery and preparation for manufacture. You can see here that I've added in some of the original mounting faces and bearing surfaces, and the next step is to use the Fit tool within the Polynerbs tab to automatically fit this geometry with Polynerb surfaces. This tends to give a nice, smooth, organic appearance to the model, and in many cases this is what we want. However, if we want to have more discrete or constant cross-section members, we can also selectively remove some of the control cages from the Polynerbs geometry by double-clicking on these rings and then deleting them. This will give a more consistent cross-section and simplify the member. In preparation for this activity, I've created some geometry purely for the purposes of cleaning up the model. So these red bodies are used to cut out the known faces from the model to make sure those are accurate and parametric surfaces. And then I've also got CAD of the original bearing surfaces, which I'm going to reintroduce to the model to make sure those are exactly as designed Because this is a symmetric part, I'm actually going to remove the half that I haven't been working on. And then use a mirror operation to make this part symmetric about the central plane. And that's what you can see here. I use a Boolean union to join these two pieces together, and this is now one model. Using the rendering capability in Inspire, we can now see that we have a nice, smooth model that has sharp features that are accurate and tolerance where required, and the more organic and skeletal appearance where that's necessary.